So, we continue with the fundamentals like we did last time, and we looked into the range of audible sound in terms of frequency as well as intensity. And if you recall, we said that 10 to the power minus 12 watt per meter square intensity, that is the lowest we can hear, threshold of audibility roughly, and 1 watt per meter square is threshold of pain. Beyond that, it will, you know, you will feel a pain. Also, we said that roughly around 20 to 20 kilohertz, there is a range of frequency. So, audible range of frequency. Now, this is physical, physically measurable things, or if not directly, indirectly. But then human response is somewhat physiological issue, a bit of feeling, subjective issues are involved. So, basically we got to look into the ear a little bit, right. Human ear, it looks something like this, right. So, you have a canal, external, so this is the canal, and this is the membrane or diaphragm, where the air, like vibration about the mean position of equilibrium, acoustic waves, they will come and impinge upon it. Then this is connected to 3 bones actually. This is one, and this is another one. We are not going to look into too much into the physiology of it, but this is the diaphragm, this is very important, and these bones actually transmit these vibrations, right, through this canals and all that to auditory nerves actually. This is of course a collia, which is again sort of a spring like bone. So, finally, they transmit this nerve transmit these signals to the brain, and then brain recognizes. It recognizes, like you have got what do you call, there are there are softwares for ears together, right. So, which will actually recognize your voice and then train through neural network or whatever it is. So, this is already trained, so it can actually recognize the voice. So, the signal goes through this. So, you see there is something physiological about it. So, it is actually the vibration in the air which goes to the diaphragm, which is connected to certain bones, which will transmit this longitudinal vibration and then convert them into electrical signals, go to the brain, right. So, that is what is written here. The outer ear collects sound waves and channels them down to ear canal, where they cause the eardrum to vibrate, the diaphragm I was talking about. This in turn causes the middle ear bones, collectively called ossicles or individually known as hammer, anvil and stirrup, to move, increasing and amplifying the vibration and transmitting that to the inner ear, the collia, right. And then followed by this is the inner ear resembles a snail shell, that is what I was showing you, containing fluid. The vibration causes the fluid to move, setting tiny hearing nerves in motion. An electrical signal is then sent along the auditory nerve, which the brain translates into sounds that we hear, right. So, that is what it is. So, there is something, so this is that collia, snail shaped, which has got fluids. The bones, ossicles, these are the ones, must be the Latin names, okay, fine, and these are the nerves which actually transmit. So, that is the idea. So, therefore, ear does not exhibit linear response to intensity, right, with either frequency or sound pressure level or intensity, whatever we call it, and thus people do not recognize equal amounts of sound energy at different frequencies. Our ear is frequency sensitive, that we have seen, because at low frequencies, very low frequencies, below 20 K we practically do not hear, and above 20 below 20 hertz we do not hear, and above 20 K we do not hear. So, therefore, it is sensitive to frequencies, and it is sensitive to frequency, therefore, even same intensity you do not perceive as equally loud. same intensity, you know, when we are saying threshold of audibility, that means you can barely hear. Pain means it's very loud, but this loudness or sensitivity of the ear to intensity varies with the frequencies, right. The simple measurement of energy or pressure is not enough to noise if you want to assess the noise. You must know at what frequency the pressure or intensity is. Then you can, you know, estimate what would be the perceived loudness or something like that, right. So, the subjective aspect of human ear response must be taken into account, and people have done such experiments and they generated what is called equal loudness level contour, equal loudness level contour. I have defined the decibel other day, if you remember, sound intensity level, pressure level, etc., etc. And this is what we said, sound pressure level would be, this should be LP, not LW, this should be LP, 10 log P square by P square reference in decibel, and this is what is equal loudness level contour. I am not very sure how much you are able to see it, but in this axis we have got frequency. This axis we have got frequency. This is a form, we can see that this is in terms of curve. So, this axis is frequency, this is 10 kilohertz, this is 5 kilohertz, this is 1 kilohertz, 500, 10 hertz, you know, something like this. So, this is in log scale, frequency always we put in log scale, and this is sound pressure level, that is in dB. So, it is already relative scale dB. So, this dBs are 0, 10, 20, 20, 40, etc., etc. They are, you know, equal distance, because already logs we have taken log and then relative scale. So, what we observe is that at low frequency, this is the threshold level that you can just barely hear. So, you need high dB to just barely hear at low frequencies, while at say something like, you know, this is 2000 or 2K, 1000K, you are somewhere there, and somewhere here this is more sensitive to it. You require much less dB, for example 0, this is 0 phone actually 0, this is you just can hear, by definition this is our 0 because the relative scale 0 dB. So, this is the threshold line. Similarly, you can see that curves are here, this is 40 dB at 1K, at 1K 40 dB, this line is 1K. So, 1 kilohertz, let us take 1 kilohertz as a reference, where you find near that the sensitivity is maximum. The least dB level, here the dB level, say let us say this is 20 dB at 1 kilohertz, and the loudness that you perceive, you will require 60 dB to hear it at this frequency, right, or let us say 50 frequency, 50 you need, you know, for 20 you would need actually 70 dB. So, 70 dB at 50 hertz is equal to 20 dB at 1 kilohertz, 1000 hertz, right, because ear is more sensitive to higher frequencies such as 1 kilohertz, but beyond that again it, you know, it shows this kind of behavior, right, and as we are going towards the ultrasound range. So, at low frequencies sound is, I mean ear is not as sensitive as 1 kilohertz or, you know, 1200 or something like that, 5000 hertz. So, sensitivity of ear is less in low frequency, but you see, you look at this one, this curve, which is 120 hertz at 1K, 120 hertz at 1K, the variation is much less. In other words, when level increases significantly towards threshold of pain, effect of frequency gets somewhat reduced. Only here you find, you see this curve is stiff, this curve is somewhat less stiff, right. So, 120 at 1K. So, this values written 20, 40, 60, 80 at 1K. So, we take 1 kilohertz as a reference point, and the decibel level at that, say 20, the loudness of the 20 decibel level to 20 dB at 1 kilohertz, we call it 20 phone. Loudness that one would perceive, this is from subjective experiment on healthy people. taken from the book by Barnack, or this they are in many books actually. Barnack has got set of acoustics, classical acoustic books actually written. So people have done experiments on healthy subjects. Ask them to like we talked about thermal comfort. Remember, so you know same thing, similar here, loudness level, the comfort, acoustic comfort you are looking at, noise, comfort against noise. So people who are subjective, healthy people who are subjected to noise, and frequency is varied, say decibel level, you vary the frequency, and say 1 kilohertz, you say you keep it at 20 decibel, then change the frequency, lower the frequency, and increase the decibel level. People will respond, okay, this is equally loud as 20 dB at 1 kilohertz. So that's how this sort of curves are generated, and these are 20 unit of loudness is phone, which is not exactly intensity. It is the loudness of 1 dB. One phone is loudness of 1 dB at 1 kilohertz, which would actually require much higher dB at 50 hertz, or loudness of 20 dB at 1 kilohertz is 20 phone. Loudness of 40 dB at 1 kilohertz is 40 phone, which will correspond to something like 70 dB in 100 hertz, because following the equal loudness level contour. So these are called equal loudness level contour. Equal loudness level contour, this 120 phone, this 100 phone, 80 phone, and so on and so forth. So 80 phone curves means loudness, curve for loudness corresponding to 80 dB at 1 kilohertz, right? 80 dB is 1 kilohertz. So quite often you will find we express the noise not exactly simply in linear dB as we call it. This is linear dB, measurable, because sound pressure level can be measured easily by various kind of transducer, amplify it and you record it. So that will give you linear dB, no variation with frequency. But you can have frequency sensitive amplifiers which will amplify selectively, filter it out, so selectively at higher frequency it will, at certain frequencies it will amplify, other frequencies it will amplify less. So these are used in sound level meters. I will just come to this, and you will find that, like you would have heard, the court order is that during the Diwali time noise level should not exceed 60 dB, right. Well, like the OIT noise level should not actually increase 60 dB outside the OIT, which it does, sometime it is maybe 100 dB. So that's so loudness is phone, and as I defined, one phone is 1 dB at 1 kilohertz, loudness of 1 dB at 1 kilohertz. 100 phone means loudness of 100 dB at 1 kilohertz, which will be more dB, more pressure, pressure level has to be higher at lower frequencies. Slight at higher frequencies, again it reduces down. So you can see that the curve tends to go up. So your sensitivity reduces. Sensitivity is maximum here. Sensitivity is maximum somewhere, but then we have taken a little bit away from it as a reference frequency, that is 1 kilohertz. So this is the equal loudness level contour for 120 phone. It is 120 at 1 kilohertz, 1000, 1 kilohertz 120, and the sensitivity is more, somewhere around maybe 2000, 2500 or 3000 hertz, and beyond that again sensitivity reduces. So but loudness level has been defined with respect to 1K, right. There is another unit called zone. We will not look into them much, because physical measurable things are important from our design purposes, but if you want to convert, let us say something related to human ear also, your sound level meter must be able to take care of this kind of thing. We will see that how it occurs. Sorry? PRMS, pressure, PRMS, because I said that I will talk, whenever I say P, I will mean PRMS only, and P reference, this is what we defined in the last class, right. P reference is 2 into 10 to the power minus 5 Pascal. 2 into 10 to the power minus 5 Pascal. We have actually, you can find it out. I didn't. So you see, what we said was, how did we define the sound intensity level? We defined sound intensity level. Remember, sound intensity level SIL, which was 10 log I by I reference. And how much was I reference? 10 to the power minus 12 watt per meter square. 10 to the power. So, this is this I by I ref is I by I ref is nothing but we are taking as 10 to the power minus 12 I, that is what it is, right. Now, I am talking of reference pressure. Now, how is I related to pressure? P square by rho C. Remember that, because we said that I, we integrated it I into u, I mean velocity or particle velocity as a function of time, both as function of time, because that gives me the power, sorry, pressure multiplied by, I said wrong, pressure multiplied by, this is was integrated from over the full cycle and then divided by time period 0 to t, these are all function of t dt, that is what it is, right. And v, that velocity can be written as, that is right. So, therefore, I would have integrated p square by, and we found out the RMS, we said that. So, basically intensity is right, p RMS square divided by rho c, right. And now I am talking of reference, I reference. So, I reference is 10 to the power minus 12 is equals to p ref, I will call it p ref square, and rho c was 415, standard temperature and pressure, that is what I said. So, you can find out now p ref will be equals to 415 into 10 to the power minus 12 to the power half, right, and this will be equals to 400 will be how much, 20, roughly 20 something, I mean 21, 22 something of that kind, or write 2.0 into 10 to the power 1 into 10 to the power minus 6. So, this will come into 2 into 2 point something into 10 to the power minus 5. So, that is what you can find, that P reference comes out to be that, right, P reference comes out to be that, right. I think I will have more discussion on this later on. So, so that is what it is. So, we are saying P reference is this, right. So, phone we define, phone is another unit of loudness which is 2 to the power phone minus 10, phone value minus 10 divided by 40. I do not think I will go into this further because we are not going to use this. Pitch is what? Pitch is the frequency as we perceive. Its physical thing is frequency, but the way we perceive. For example, like as you can see, this is an aeroplane, it's around 500 hertz, right, and this is a motor car of the good old days, truck somewhere there, somebody snoring is here, right, and some bird singing is somewhere there, whispering, concrete cutting machine and so on. So, this is a typewriter, telephone of the good old days. Today, of course, you have all varieties. So, you see, you can do you see something interesting? This is the leaf, the plant whistling, right, and natural, this is natural, this is natural, this is definitely artificial. So, all these are relatively artificial, this is very much natural, and our ear is most sensitive to the natural things. See, the sensitivity of the ear is very close to this. This is because it has evolved over the millions of years of human evolution process. We adapted ourselves to the natural sounds, right, river rapids, where it is a small waterfalls or something like that, or similar sort of thing actually. So, they human ear actually. Similarly, the eye is most sensitive to that light which is maximum in the sunlight, yellow, right, somewhere around 500 or 550 nanometer, that is very sensitive, yellow our eyes is sensitivity is eyes very much. Temperature, similar things I do not think I will be able to say, but it follows that Webber-Fechner's law. So anyway, coming back to this, pitch is the way you distinguish frequencies. Your ear distinguishes the frequencies. So these are the low frequency thing somewhere there, right? So instrument got to take care of all this, measuring devices, right? After all, I want to specify, when I am designing for noise control, I want to specify, well, noise level should not be more than this. Now this I could have done by doing it in terms of simple dB, linear dB, without any, without being sensitive to frequencies. So this is called linear dB, where no modification, whatever is measured by your sensing device, transducer, you just amplify them, and that's what you get the pressure level. Pressure you can measure. So pressure square divided by P reference square, and 10 log of that would give you the level of the decibel level, right? Now, but as I said, your ear is sensitive, less sensitive to low frequency. So what I can do? I can make amplifier systems such that they will selectively or amplify less at low frequency, like this. I will come back to this. Something like this. I have a microphone which is basically the transducer which will pick up the sound. Then I have some pre-amplifier system. Obviously, first you would have, nobody does these days, but good old days we used to actually assemble transistors, because good old days, I am talking of no televisions really in a big way. So student level hostels, people will do soldering, purchase a printed circuit board, put in the transistor and the capacitor and all those. Today you don't do this, you don't have to, but then there is a pre-amplifier stage. Then these are weighing networks. These are some kind of electronic networks. What they will do is, if you choose A, it will amplify selectively more at higher frequencies and cut down at lower frequency. This B does this a little bit less at lower frequency, and C does very little, whereas linear does not do anything, it will straight away amplify equally. It does not look at the frequency first, and do not amplify frequency selective. So I will come back to this again. So these are actually filters, sort of weighing networks, these are used, and you have linear, no filtering. A weighing network, it cuts down, practically follows about 40 phone curve. It cuts down the sound at low frequencies more. So these are negative values. That means if actually is 100 dB and you are following A weighing, and at 100 hertz it will display 70, near 72 or something like that. And at 1000 hertz, of course, there is no change. At 50 hertz, because this is log scale, it might show something like 60. But if you choose B weighing network, same sound, B weighing network, it will show something like 90 for 100 dB, right, something like 90 for 100 dB, and if you have chosen C, it will show you 100 only. So can you relate this somewhat related to this sort of curve we had? You see, if you have predominantly high level of sound, then you might use C weighing. If you are predominantly somewhere in the mid range, you might use B weighing, but you have to pre-decide which one you want to use. A weighing is commonly used for most of the noises, because you might have somewhere, levels could be somewhere around this zone, 70, 80, maybe 100 also, somewhere around this zone. So you will find that whenever noises are specified, somebody will specify dBA or dBB or dBC, usually dBA. So you will find the codes will say the noise in a residential area should not be more than, traffic noise or external noise should not be more than 45 or 50 dBA, right, something like that, and inside the room it should be still lower or whatever it is. So this is specified in that manner, the dBA values. dBA means that at low frequency, ear can tolerate low frequency, so you can have higher dB. So, at every frequency it finds out based on this curve, sort of curve, and sum them up together, the dB total intensities and filtered intensities or pressure levels are summed up, pressure level squares are summed up, and then equivalent dBs are found out. So, dBA, dBB, dBc, these are used for, or dBA is largely, you will find that like when the court says, or NGT, National Green Tribunal or something, it says that noise level should not be more than 60 dB in a in a residential area during festival time of crackers, festival of cracker time or something like that, or if you have some sort of a any kind of microphone usage, it should not be more than that. So, these weighing networks are used to simulate actually human ear response, right. So, this is their filters actually, and this is how they are, as I said. So, you choose basically. So, now see this is dotted line means you can choose. There is a switch, toggle switches could be there. So, you choose either this filter or this filter or this, or linear means it will show then amplifier and then display. So, display will be lower, actual dB is higher, measured pressure level is higher, but display would show less after going through these processes, right. ABC weighing networks are based on A is 40 phone. So, it follows 40 phone curve, like I said the 40 phone curve. So, if you from the 0 level, if you take that dB values at every frequency, you get 40 phone curve. This is 70, B is 70 phone curve, and C is 100 phone, equal loudness level contour respectively, right. So, that is how actually it takes, all right. A most often used, and the level measured is denoted by dB or dBA. That is what you will find, that like all sorts of specifications would be many a times in terms of dBA or the way it is written. Sometimes people use D weighing network also for aircraft noise assessment, and there are other ways of assessing the noise as well. I will come to them. So, these are some of the descriptors, but there is this is at like at any instant I was talking about, right. But if you look at, let us say you are next to a highway or an arterial road of a city, which also American ways of calling it is highway. Highway in the city also you can have. I mean, one is of course you have grade separated highway, which you find mostly Europe, even in the city, if the highway passes, grade separated, you do not enter there, right. But America, everything is highway. Obviously, you enter, you do not get out like that, they are grade separated again. So, highway or arterial road, if you are close to that, the noise will be there for the whole day, right. So, I must have a way to measure the noise, average noise level in some manner. I must have a way to measure the average noise level in some manner. If I am to design something, some noise protection devices, some things, then I must have an idea of average noise level or peak noise level and least noise level. Distribution of the noise over the period of time, right? Distribution of the noise over the period of time. So, average, sometimes time average we use, measured during 6 am, 6:30 am, 7 am, etc., until 12 midnight and back maybe 24 hourly, or if there is no noise after midnight, then you can leave it at that point. So, measure it over the whole period of time and you might actually take an average. But remember, you cannot add the dBs because they are relative scale. So, 60 dB plus 60 dB is not 120 dB. What you can add? You can add intensities, this is a scalar quantity, or you can add P RMS square, because intensity is related to P RMS, P square divided by rho c. So, you can add P square, because P is a function of time. So, there is a problem, you can't add like that. So, dB cannot be added. So, you can integrate, when you are integrating, you can add P by P ref delta t, but 20 log will come here, right. I mean, this square you could have integrated, because these are all reference. I mean, RMS, both are in RMS time terms. So, 20 log if you measure from 0 to t dash time, divide by 1 by t dash time, that will give you the average level during that period of time, L equivalent, that we call as L equivalent. L equivalent, right. So, and P by P reference is how much? NT log of 0.1 LP by 2. Okay, because why it is? We said that P square by P reference square, right, P reference square 10 log of that gives me SPL dB value. So, if I know LP, I mean I am calling this as LP, right. So, LP divided by 10 is 0.1 LP, 0.1 LP, right, and NT log of what, 10 to the power this, or NT log of this, NT log of this, NT log of this is equals to P square by P reference square, right. Now, if I P reference square, or I could have actually divided this by, because this could have been 20 log, like this I could have written 20 log P by P reference. So, divide this by LP by 2, that is what I am doing, LP by 2 multiplied by 0.1, and NT log of this is P by P reference. P by P reference is this. We can calculate back. Just we will do that again. Maybe I will just do it from here again. I will just explain this again. So, you can have a quick break and then take some questions from you, and then we will come back again.